Large earthquakes happen suddenly and unpredictably. Therefore, they usually cause serious disasters.
When an earthquake strikes, P wave comes first, and then is the S wave.
However, what will happen after S wave? Hello everyone, I'm Huang Weishen.
I'm Zheng Junchen. We're from Taiwan, affiliated senior high school of National Taiwan Normal University.
And the name of our project is Study of the Surface Trapped Seismic Waves in Southwestern Taiwan for Geohazard Prevention. Taiwan is located at the junction of the Eurasian Plates and the Philippine Sea Plates, and is continuously threatened by large and devastating earthquakes. For example, Tainan earthquake happened in 2016, and a 17-story residential building collapsed. And in 2010 Jiaxing earthquake, a high-speed rail train was derailed. In these two earthquakes, when we see the seismic data on the CWB website, we observe a lot of low-frequency waves after P wave and S wave in seismograms, especially on vertical component. After looking up literature reviews, we believe they are surface-trapped seismic waves, a kind of generated surface wave, resonated by body wave that passed from deep, harder rocks to shallow, softer sediments.
Our seismic data is collected by Taiwan Strong Motion Instrumentation Program, or TSMIP for short. More than 800 stations collect high-quality recordings of strong earthquake since 1992 in Taiwan. We use the software Seismogram 2K to analyze the seismographs. When we put the seismographs into spectrogram, we can see the distribution of intensity of each frequency at each time. And then we can see that low frequency and long duration time is the feature of trapped waves. We use spectrum to pick up the trapped wave's dominant frequency. The function of spectrum is to calculate the intensity of each frequency, and the peak is the dominant frequency that we need. After spectrogram analysis of Tainan earthquake, we can see that the trapped waves only develop in plain areas. We can see that the line 1 and 2 both develop the trapped wave. But the line 3, the one that travels through mountain areas, didn't develop any trapped waves. And these phenomena show the effect of underground sediments. Next, we try to calculate the velocity of trapped waves. Since the time record of TSMIP are not entirely correct, we made the relative arrival time to plot travel time curve of all stations record. And the result shows that the velocity in line 1 is faster than line 2. Only 12 stations recorded with accurate time and help make the precise travel time curve. And now we obtain the velocity of P wave and S wave to compare with past research. What's next? We plot the dominant frequency chart according to position of stations, and the dominant frequency decreased from east to west. They're from 0.25 to 0.8 Hz. And also, we observe some stations have obvious higher value than the nearby station, which is hard to explain. Furthermore, the longer the shaking, the more serious the disaster. Here's our method to calculate duration. First, we remove the noise under 1 gale, and then we sum up the whole energy, and then pick the timeline from 5% to 95% of whole energy to be our duration time. Here's the result of duration. The duration of trapped wave ranged from 20 to 95 seconds. We observe the longer duration mostly distributed in coastal areas, but there's some problem while analyzing the duration. Some stations didn't record the whole event, which caused difficulty in analyzing the duration.
According to many other research, trap waves are generated when seismic waves pass through the low-velocity layer, and the thickness of such layer will affect the dominant frequency of the trap waves. That's what is shown in this formula. It is assumed that the layer is flat and homogeneous, but actually, the layer is not flat or homogeneous. So the depth we calculate just indicates the total effect of low-velocity layer. We call it the effective depth, HE. As for the result, HE ranges from 100 to 400 meters, and the depth in Tainan is the deepest. Besides, we compare our results with microtremor measurements. Z0.6 and Z1.0 are derived from microtremor measurements. They can indicate the thickness of low-velocity layer that is corresponding to sedimentary thickness. In contour maps, the distribution of HE and duration are both similar to Z0.6 and Z1.0. Moreover, the low HE and duration area in circle correspond to the shallow low-velocity layer in Z0.6. Our results of dominant frequency may provide a parameter for resonance frequency with buildings. If the wave's frequency matches buildings' natural frequency, they will resonate and cause bigger damages. We use the empirical formula in here to calculate, and the results show that the trap waves could resonate with the buildings 10 to 40 floors tall. We also find a similar trend while analyzing the 2010 Jiaxing earthquake and the 2012 Wutai earthquake. Here are the HE results of these two earthquakes. By the way, according to other studies, the development of Taiwan high-speed rail in 2010 Jiaxing earthquake was due to the surface trap seismic waves in here. It will be an interesting topic for our further research. For the last part of our presentation,
we would like to conclude our research.
To reduce the geohazards caused by earthquakes, we analyzed a kind of surface wave, surface trap seismic waves. They are resonated due to the low velocity layer. If the layer is thicker, the frequency of trap waves will be lower. In spectrogram, we observe the trap waves in 3 earthquakes, and the strongest waves were all detected in Tainan. The dominant frequency of trap waves decreased westward, and the duration increased westward, which is highly correlated to the increasing presence of the trap waves.
In Tainan, the depth HE is the deepest. Our results also correspond to the microtremor measurement, especially Z0.6. The analysis of 2010 Jiaxing earthquake and 2012 Wutai earthquake both show similar trend.
Our study indicates that the thickness of the unconsolidated sediment is the major factor in the development of the trap waves. It will be a quick and efficient survey to estimate the impact of side effects, like the index of shallow geology and the resonance frequency of buildings. This is the end of our presentation.
Thank you for your attention.
Bye-bye.